welcome to the 9th video, 5 systems in the wire. So in this video, for 8 chapters as we talked about, we have built the tools and studied the ideas. No more theory now, but I want you to take you on a tour of practical applications. 5 systems running in the real world today, each assembled from exactly the pieces this series has been putting together. And for everyone, we will ask the same 4 questions. As you can see, problem, data, what method, and problem data method basis we are honestly asked, does it actually work? What is the problem? What data do they have? What method do they use? Does it actually work? So let's move on. So if we look at 8 videos and this video, we have to start where we start, because it is where we have to think carefully. The problem, the first use case I'm going to talk about, wind is worth less to a grid than steady, predictable power. So we have like this problem, and data can be with the forecast plus year of turbine records, and the method to predict that, deep neural network from chapter 3, forecasting each farm's output 36 hours ahead, which is exactly probabilistic forecasting of chapter 8. So in here, the outcome is by turning those forecasts into firm day-ahead commitments. So Google and DeepMind raised the value of 700 megawatts of wind by roughly 20%. So the same wind, more value. So purely from no wind in sugar. So the first use case, we are going to see where we began. We are going to predict. So this system 1 is a valid use case that we can see in many countries, and Google and DeepMind, they have done it together. Second use case, operating the high voltage grid itself. So this problem is keeping a transmission network stable as renewable push it hard, deciding which switches to flip when a line starts to overload. So the data like we get is high fidelity simulator of a real grid built by RTE, France Grid Operator. The method is reinforcement learning agents from chapter 5, often relevant as graph from chapter 6. So I'm referring these methods, and learn topology moves no human ever wrote down. The outcome is, let me be honest here, this one is still largely in lab environment. Through the learning to run power network challenges, agents have learned to run simulated grids under real stress. So in this scenario, 2025 RL to grid benchmark show the best agents still struggle to respect hard safety limits. It's a very important outcome. The direction is real. It is driven by actual grid operator, and it is not yet trusted to run the live network alone. So in this scenario, this is a very good indicator that we are still expecting. Third system is thousands of ordinary homes into single power plant conversion. The problem is rooftop solar and home batteries are scattered across the city. Each one its own, useless to the grid actually. But the data, if we are looking at it, live electricity prices, every battery charge level, local demand, etc. And the method what we are doing here, we are aggregating them all and let software dispatch every battery at once using Autobidder. So charge when power is cheap, discharge when it is scarce. So storage control of chapter 5 we have talked about. The outcome is Tesla's virtual power plant in South Australia links thousands of solar and battery homes, 6,500 plus homes actually. So its Autobidder software trades their combined power on the national electricity market, which is a huge deal in this scenario. More than 6,000 homes, as I mentioned, acting as one power plant big enough to drive a small power station. So we can understand the significance of this example. So moving on, keeping the hardware healthy is the motive of system 4. The problem is a large solar farm has hundreds of thousands of panels, and a single failing cell can quietly bleed away energy for months, completely unseen. The data we take in aerial thermal and visual images, millions of them, sometimes captured by drones that live on the site launch themselves. The method is computer vision from chapter 3, spotting the hot failing cells and pinpointing each one down to the exact module. So moving that, the outcome is like Raptor Maps has analyzed hundreds of megawatts of solar this way, operators like NG and Inel Power. So in this scenario, on sites watched by the autonomous drones, average power loss dropped around 5% to 3%. So this is a very significant use case, and the gap is real money, the real clean energy pulled back from the dark. So in this scenario is also significant example that we can take. On to the ninth. So as I mentioned, this also like a good use case that we can use. Moving on to the fifth one, back to forecasting, but now inside a national control room. So in this scenario, problem is single passing cloud can drop a country's solar output in minutes. So the data that we are looking at this to cover that uncertainty, grid operators keep fossil fuel plants burning just in case. So that's a scenario. So live satellite images of clouds drifting across the country is a good data source that we can use in this scenario. And the method is like deep learning from chapter 3 again, reading those images to nowcast the sunlight minutes and hours ahead. So we are calling as nowcast, and outcome is working with Britain's grid operator, the number of it common time and fix with the solar forecast in this scenario. And here's the beautiful part, that in operator's own words, they are mentioning like this: the more confident the forecast, the less backup power they have to burn. So more confidence, less backup. That is the entire thesis of chapter 8, spoken by the people keeping Britain's light on. So this is a very larger scale cost efficient way of solar power. And to be fair, we have now 5 systems, and look at what they have in common. Every single one is built from the pieces we have spent this series assembling: deep networks, reinforcement learning, graphs, forecasting, computer vision, so these chapters. And notice something else, something honest, where not one of them runs entirely alone. It's always a combination, it's always a mixture. Everyone has human operator in the loop, hard safety limit, a person who sign off everywhere. So these are not the machines that replace engineers. These are actually made engineers fast, sharper, and able to see more of the grid. Which leaves exactly one question: how do you build one yourself? What are the actual tools? So that is the final chapter. Let's finish this off. Thank you for hearing me out.